Hello dear students, welcome you all. Today we are going to start Electronics 2 course of MSc 4th semester. In this course we have three sections. This is the syllabus of this MSc 4th semester Electronics 2 course. You can see here we have three sections, section A, section B, and section C is not visible here. Section C is basically fabrication of integrated devices. We will start from section A. In section A, we have different topics. All of them are based on analog and digital systems. Uh, in this section, the first topic is analog computations, and then we have active filters. We will start from active filters. Then after we will come back to analog computations. In this unit, we will also do comparators, logarithmic and anti-logarithmic amplifier, sample and hold amplifier, waveform generators, A to D, D to A conversions and their applications. All these things are mentioned here. Today, right now, we are going to start from filters. Students, first of all, we have to understand what is the concept of filters and why they are used in electronics, what is their role. So, uh, if I talk about exclusively about the filters, you might have gone through filters in your BSc final class, where it was mentioned in electronics uh, book in, I think, chapter number 3, PN junction diode, rectifiers and its applications. In that course, basically, filters were the that were used there. They were very simple kind of filters. They were passive filters basically, uh, and they were used to make the output of a rectifier smooth. Smooth means when we use a rectifier. Rectifier is basically used for the conversion of AC to DC. But when you convert AC to DC, you might have seen in case of rectifiers that the output that we obtain from a full wave rectifier is not a pure DC, but rather it is a mixture of AC and DC. It contains ripples. In order to remove all those ripples, those frequencies, we need a filter, because if we use that output that we obtain from a full wave rectifier to drive any electronic appliances, then that will not work properly, because that is not a DC, pure DC. We have to smooth that output, and for that purpose we use filters. In BSc final, we have learned about the passive filters. They were, choke filter, capacitor filter, and then LC filter, then pi filter. All those filters were making the use of simply a capacitor and a inductor. So, first of all, we will understand what is a filter, what is the difference between an active filter and passive filter, what are the different types of filters depending upon their operation, and then we will come exclusively to the active filters which are mentioned in this course. Right. Filter, if I give a definition to a filter in electronics, then filter is basically a electronic circuit that is used uh, for selecting a desired frequency in a given spectrum of frequencies. Right. Now this filter can be of two types, active filter and passive filter. If I talk about passive filter that you have learned in your BSc final class, then passive filters are those filters which make the use of passive components in electronics. You know very well that in electronics we can have two type of components. One are active components and other are passive components. Active components means those components which are capable of doing the amplification, like transistor, NPN transistor, PNP transistor, junction field effect transistor. All those are active components. Operational amplifier. These are active components. So if we make the use of active components in the designing of a filter, then that filter is called active filter. But if we use only passive component like capacitors, inductors, resistors, then in that case we call that filter as a passive filter, because that filter is not capable of doing the amplification, right? So those filters that were mentioned in BSc final year electronics course, that those were all passive filters, right? So I'm hopeful that now this is clear, that what is the difference between active filter and passive filter. Now I'm coming to the different types of filter based on their capability to select the desired frequency. So according to that, we have a low pass filter, high pass filter, right? Uh, this is low pass filter. Here you can see uh, this is cutoff frequency FC, right? So all those frequencies which are below this, right? This which are below this FC, they are allowed to pass through the filter, right? And after this point, uh, the gain of the amplifier will reduce gradually and it will ultimately become zero. It means all those frequencies which are above this cutoff frequency, they will be uh, stopped by this low pass filter. It means all this band is pass band and this band is stop band, right? Similarly, we can have a high pass filter. In high pass filter, now you can see here clearly that all those frequencies which are above FCs, because if we look at the frequency response of this high pass filter, then it is clear that this gain is high and then it is stable in this region. What if we go below this frequency, means less than this frequency, then the gain again reduces and ultimately it becomes zero. It means all those frequencies in the signal which are above this of FC, they are allowed to pass through the filter, and other frequencies will be stopped. So this is called a high pass filter. Now I'm coming to the third category. This is band pass filter. Now in some applications we require that a band of frequency should be allowed to pass through that filter. For example, if we are dealing with the audio frequency range, in that case we have a frequency uh, uh, that is in the form of a band 20 hertz to 20 kilohertz. So for that we require a band pass filter. Band pass means that band of the frequency will be allowed, and all those frequencies which are below this lower cutoff frequency and which are above this upper cutoff frequency, they will be stopped. Here and here you can see the gain is very low. It reduces and ultimately it becomes zero. Here it reduces and it becomes to zero. This is called central frequency. So this filter is, if we use this kind of filter, this will be called as a band pass filter, right? Similarly, we have a band reject filter. Band reject means we are now going to reject a band of frequencies. It is exactly opposite to the band pass. In band pass, we are allowing a band of frequency, but in this case, we are rejecting a band of frequencies. So here you can see clearly that this graph is, the graph is reducing as we are going closer to the central frequency in both the regions, whereas in here and here it is stable. So means in these two regions the gain is high, whereas in these in between these two regions here in this particular band the frequencies, the gain is very low, and this is called central frequency. So this is called band reject filter or notch filter, right? So now this is the classification of the filters based on their ability to select a particular frequency or a range of frequencies, right? So now I'm coming to the active filters, how active filters are designed and how they work, right? Because in our syllabus we have mentioned, they have mentioned active filters, right? So active filters, now as I told you that in case of a filter we are using some basic components, right? So in all type of filters the basic component is a capacitor and a inductor, because these are two electronic components which are capable of blocking either AC or DC, right? Uh, so if we look at the basic functional unit of any filter, then it will be a capacitor and a inductor. This is a capacitor, right, having capacitance C. We know that in case of a capacitor, the capacitive reactance is 1 upon 2 pi F C. This is here F is the frequency of the signal or alternating current, and yeah, only we can say current, and C is the capacitance of the capacitor. So you can see from this expression, this is capacitive reactance, right? Capacitive reactance means the opposition offered to the flow of alternating current or alternating signal through this capacitor, right? So if frequency F is 0, as it is in the case of DC, right? For DC, F is equal to 0. So for DC, this capacitive reactance, right? It will become, I can write it as XC. It will become infinite, right? Infinite. So for a capacitor, the capacitive reactance is infinite in case of DC. It means for DC, it is behaving like a open switch, right? So if we connect a capacitor in a circuit in parallel, then it will, let's see here, that this is the signal that is coming from this side toward this side. You can take it like a alternating current AC, because alternating current is also a signal that has frequency 50 hertz in India, right? So if I connect a, this capacitor here in parallel, what it will do now, this is capacitor, what it will do now. Here we are taking the case of alternating current. So let's see what is the case of alternating current. For AC, we know frequency in India is 50 hertz, right? So if I put 50 here, then there will be some value. It means XC is not equal to 0 or not equal to infinity. It has some value, right? Means it is providing a path. It is providing a path to the flow of this alternating current through this side, right? So it means the alternating current can flow in this way, right? Because this electronic component is providing some opposition or resistance, or we can say uh, uh, capacitive reactance, but it is not infinite, so it means current can flow. It is behaving like a closed switch, right? Now let's take the case of DC. Now in case of DC, frequency is 0, and this capacitive reactance, or we can say opposition, is infinite. It means in this case, this capacitor will behave like a open switch. So the entire DC current, that is DC, now in this case, that is flowing toward this side, that DC current will pass toward this side without going here, right? This is very important. This DC current will not go to this side. It will pass directly. So it means when we are applying this capacitor in parallel to the output of a rectifier, the DC will pass without any opposition, without any resistance. But for AC, it will offer a easy path to flow through this path, and AC will be bypassed in this way, right? And it will be stopped here at the capacitor. So it means capacitor can be used uh, in parallel to block AC component, right? And now let's see how inductor is used for blocking, DC and allowing AC to pass. Let's see the case. We have an inductor that is represented by this symbol. This is the circuit symbol of an inductor L, right? And if we talk about the inductive reactance, then it is 2 pi F L. Now you can see here. Now again the same thing. F is the frequency of the current. L is the inductance of the inductor. Now what will happen when we will pass current through this inductor? Now let's take the case. First of all, remove it. Now we are using a inductor in a circuit. Suppose it is connected at the output of the rectifier. Right? Now this is the output of the rectifier. Now let's connect this inductor here. Right? Now what will be the output here? Be output. Now if this current is alternating current, right? This current is alternating current, means AC. Then what will happen? When the AC will flow through this inductor, F is 50. 50 in case of alternating current in India. But if we are passing a signal that is of certain frequency, then this value will be different. So let's take the case of AC. It means there will be inductive reactance XL. It will have some value, right? When it will have some value, it means this inductor will offer a opposition to the flow of alternating current. It will try to block the AC, right? But if we take the case of DC, then in case of DC, F is 0. F is 0 means XL is 0. It means for DC, there is no opposition. DC current will be passed without any obstruction, without any resistance, and it will go to the output. So this is the basic fundamental principle in all filters, whether they are active filters or passive filters. The basic components, the basic functional units which are used in these filters are either capacitors or inductor. Other components are used in the circuits, but the main work is done by either capacitor or a inductor, right? So now I'm coming to active filters. We have learned what is the basic concept of filters, this capacitor and this inductor. So we learned that a capacitor should be connected in parallel, whereas inductor should be connected in series if we try to block the alternating component in the signal, right? Now let's come to the active filters. So as I told you, in case of active filters, we have active components like a transistor, for example, let this is NPN. Emitter, collector, and base. So this is NPN transistor. This is an active component because we know a transistor is capable of doing the amplification. So when we uses active components along with capacitors and filters, then the resultant filters will become active filters. But here in our course, we are going to use operational amplifiers. Now, what is an operational amplifier? We have to recall what are operational amplifiers. You know, operational amplifier is a basically electronic component that is capable of doing mathematical operations. And what is the main unit in case of operational amplifier? Again, the functional units in case of operational amplifiers are these transistors, which are working inside the operational amplifiers. So if I go to the circuit symbol of operational amplifier, you can see here. After let me erase it. Or we can take a new page, right? Right, yeah. So this is the circuit symbol that I'm going to draw for basic operational amplifier. This is called non-inverting input, V, non-inverting, and this is V inverting, right? And this is output, V output, here plus B, C, C. This is minus B, E, E, right? This is the gain of this operational amplifier A. Now this is the circuit symbol of a operational amplifier, op-amp. Now when we are using this operational amplifier along with a capacitor or an inductor, then the resultant filter will become a, this is inductor. So either we are using a capacitor or a inductor. So the resultant filter will become active filter, right? So here in our course, we are going to study active filters, and we are going to make the use of operational amplifier, right? Now here operational amplifier will serve the two purposes. One purpose is it will do the amplification of the signals that that signal is going to be filters. It will do the amplification of that signal, one thing. Other thing is any kind of disturbance, noise, undesired signal present in the signal, that will also get blocked by the operational amplifier, because this is the property of a operational amplifier. So here we are going the use of all these things, right? Uh, so in the coming lectures, we will focus on active filters, and we will start with Butterworth kind of filters. So in the next lecture, we will start with Butterworth low pass filter, right? So thank you very much.